Welcome to Quiet Universe, where we explore the profound and enigmatic aspects of our cosmos. In today's journey, we're venturing into one of the greatest mysteries of modern science, dark energy. Picture a force so mysterious, yet so dominant, that it controls the fate of the entire universe. It makes up 68% of everything we know, yet it's something we can't see, touch, or directly measure, a true enigma of the cosmos. In this video, we'll delve into dark energy's role in the accelerating expansion of the universe, how it challenges our very understanding of physics, and what it could mean for the ultimate fate of all existence. From the resurgence of the cosmological constant to the profound questions it raises about reality itself, we'll unravel the complexities of this cosmic force. So, sit back, relax, and let's embark on this quiet yet thrilling exploration of the universe together. Dark energy is one of those profound mysteries that can send shivers down your spine, not because it's something sinister or menacing, but because it forces us to confront the limits of our understanding. It's a concept that stands at the edge of our scientific knowledge, peering into the abyss of the unknown, reminding us how little we truly grasp about the cosmos. Imagine for a moment that everything you see around you, the stars, the planets, the galaxies, even the vast stretches of empty space between them, only accounts for a tiny fraction of what the universe actually is. Most of us grow up thinking of space as an empty void punctuated by bright spots of light, the stars and galaxies that fill our night sky. But in reality, all of this, everything we know and can observe, is just the tip of the cosmic iceberg. Beneath the surface lies something so strange, so elusive, that it defies our very understanding of what the universe is made of. This mysterious substance, or rather force, is what we call dark energy. It's a name that doesn't do justice to the profound mystery it represents. Dark energy is not something we can see, touch, or directly detect. We only know it exists because of its effects, like the faint ripples on the surface of a pond that reveal a disturbance in the water, even when we can't see the stone that caused them. Dark energy is like that unseen stone, a hidden force shaping the fate of the universe, yet eluding our grasp. The first clue to dark energy's existence came from an unexpected discovery in the late 1990s. For decades, scientists assumed that the expansion of the universe, which began with the Big Bang, was gradually slowing down. After all, gravity is a force that pulls things together, and with so much matter in the universe, it seemed logical that this gravitational pull would eventually put the brakes on the expansion. But when astronomers started studying distant supernovae, exploding stars that serve as cosmic beacons, they found something astonishing. Instead of slowing down, the universe's expansion was actually speeding up. It was as if some invisible hand was pushing the galaxies apart, faster and faster, defying the pull of gravity. This discovery was nothing short of revolutionary. It was as if the universe had suddenly revealed a hidden layer, a force that had been quietly working in the background, unnoticed, yet immensely powerful. This force, now known as dark energy, accounts for about 68% of the total energy content of the universe. To put that in perspective, everything we can see, stars, planets, galaxies, and even dark matter, makes up less than a third of the universe's total energy. The rest is this strange, unseen force that we barely understand. What makes dark energy so mind-boggling is not just its dominance over the universe's energy budget, but the fact that it seems to play by its own rules that don't fit neatly into our existing theories of physics. In many ways, dark energy challenges the very foundations of what we thought we knew. It forces us to rethink gravity, the nature of space and time, and even the ultimate fate of the universe. Gravity, as we understand it, is a force that pulls objects together. It's the reason planets orbit stars, stars gather into galaxies, and galaxies cluster together. But dark energy seems to act in opposition to gravity, driving galaxies apart rather than pulling them together. This strange behavior suggests that dark energy might be linked to something fundamental about the nature of space itself. Some scientists think it might be a property of the vacuum of space, an inherent energy that becomes more pronounced as space expands. This idea, known as the cosmological constant, was actually proposed by Albert Einstein over a century ago, only to be discarded by him as a mistake when it seemed the universe was static or contracting. But with the discovery of the accelerating expansion, the cosmological constant has made a surprising comeback, hinting that Einstein's biggest blunder might actually hold the key to understanding dark energy. Yet, the cosmological constant is just one of several theories. Others suggest that dark energy could be a dynamic field, something that changes over time and space, like a tide that ebbs and flows across the cosmos. This idea, known as quintessence, is even more speculative and complex, challenging us to think about the universe in entirely new ways. There are also theories that suggest we might need to modify our understanding of gravity itself to account for dark energy's strange behavior. These theories are still in their infancy, and each comes with its own set of challenges and implications. But what makes dark energy truly unsettling is what it implies about the future of the universe. If dark energy continues to drive the expansion of the universe at an accelerating pace, it could lead to a future that is difficult to comprehend. One possibility is the so-called Big Freeze, where the universe expands so much that galaxies move beyond each other's reach, stars burn out, and the cosmos becomes a cold, dark, and lifeless place. Another, even more dramatic possibility is the Big Rip, where dark energy's influence grows so strong that it eventually tears apart galaxies, stars, planets, and even atoms in a final cataclysmic event. These scenarios are not just abstract ideas. They are potential realities that force us to confront the fragility of everything we know. The fact that such an unseen force could control the fate of the universe is a humbling reminder of how little we truly understand. Adding to the enigma is the fact that we have no direct evidence of dark energy. Unlike dark matter, which at least reveals itself through its gravitational effects on visible matter, dark energy is inferred solely from the expansion of the universe. It's like trying to understand the wind by watching leaves rustle, without ever feeling the breeze on your face. This lack of direct evidence makes dark energy even more elusive, more puzzling, and more frustrating for scientists trying to pin down what it actually is. The story of dark energy is one of complexity and contradiction, a tale that challenges our most basic assumptions about the universe. It's a story that forces us to grapple with questions that have no easy answers, questions about the nature of reality itself. What is space? What is energy? How do they interact? These are the kinds of questions that keep scientists awake at night, questions that dark energy has thrust into the spotlight. In the end, dark energy is a reminder that the universe is far stranger, more complex, and more mysterious than we can imagine. It's a force that operates on the largest scales imaginable, shaping the cosmos in ways that are difficult to fathom. It raises fundamental questions about the nature of existence, questions that may not have answers in our lifetime or ever. Yet, despite its elusiveness, dark energy beckons us to keep searching, to keep questioning, to keep pushing the boundaries of our understanding. It's a challenge, a cosmic riddle that invites us to explore the depths of the universe and, in doing so, discover more about ourselves and our place in this vast, mysterious cosmos. Dark energy is one of those cosmic mysteries that seems to exist just beyond the reach of our understanding, tantalizing us with its sheer enigma. It's as if the universe has a secret, something so fundamental and pervasive, yet so elusive that it defies our very attempts to pin it down. Despite its immense influence, comprising a staggering 68% of the universe's total energy, dark energy remains an enigma, a force we know is out there, but can't directly see, touch, or detect. It's like trying to understand the wind by observing the movement of leaves, yet never feeling the breeze yourself. This is the essence of dark energy, an unseen force that quietly, yet profoundly, shapes the universe. The story of dark energy is one of discovery, surprise, and profound mystery. In the late 20th century, scientists were fairly confident in their understanding of the universe's structure and behavior. The prevailing thought was that after the Big Bang, The universe had been expanding, but gravity would gradually slow this expansion down. It was a neat and tidy model, one that fit with the laws of physics as we understood them. Gravity was the great unifying force, the glue that held the cosmos together. But then came a discovery that would shatter this comfortable picture. In 1998, two independent teams of astronomers set out to measure the rate of the universe's expansion using distant supernovae as cosmic yardsticks. They expected to find that the expansion was slowing down over time as gravity did its work. Instead, they found something entirely unexpected. The universe's expansion was not slowing down, it was speeding up. This was a revelation that sent shockwaves through the scientific community. It was as if, instead of coasting to a stop, the universe had suddenly decided to step on the gas. Something was out there, something powerful enough to counteract gravity, pushing galaxies apart at an accelerating rate. This something was soon given a name: dark energy. But what is dark energy? The truth is, we don't know. We can infer its existence from the way the universe is expanding, but we can't directly observe it. It's not something we can see or measure in the traditional sense. Unlike dark matter, which interacts with gravity and can be detected indirectly through its effects on visible matter, dark energy is even more elusive. It doesn't clump together like matter. It doesn't seem to interact with light, and it doesn't produce any detectable emissions. It's everywhere, filling the universe like an invisible ether, yet it's completely intangible. It's as if the universe is filled with a kind of phantom energy, a presence that can't be seen or felt, yet is profoundly influential. The mystery of dark energy lies not just in its invisibility, but in its sheer scale. It's not just a small part of the universe. It's the dominant component, making up nearly 70% of the total energy content. This means that everything we can see, every star, planet, galaxy, and particle, makes up less than 5% of the universe's total energy. Even dark matter, which makes up about 27%, is dwarfed by the vastness of dark energy. To grasp this is to realize how little of the universe we truly understand. We are, in a sense, living in the shadow of this immense, unseen force, one that shapes the very structure and fate of the cosmos. One of the most profound aspects of dark energy is how it forces us to reconsider our understanding of the universe at the most fundamental level. For centuries, physicists have developed theories to explain the behavior of the cosmos, from Newton's laws of motion to Einstein's theory of general relativity. These theories have been tested and confirmed by countless experiments and observations. But dark energy doesn't fit neatly into any of these existing frameworks. It's a force that seems to defy our current understanding of physics, a puzzle that has left even the most brilliant minds scratching their heads. Some scientists have proposed that dark energy might be a property of space itself, an inherent energy that becomes more pronounced as space expands. This idea, known as the cosmological constant, was first introduced by Albert Einstein in 1917 as a way to balance the equations of general relativity and keep the universe static. When it became clear that the universe was actually expanding, Einstein famously dismissed the cosmological constant as his biggest blunder. But with the discovery of the accelerating expansion, this idea has made a surprising comeback, suggesting that Einstein's mistake might actually hold the key to understanding dark energy. If the cosmological constant is indeed real, it would mean that the energy of empty space is not zero, but has a small, positive value that drives the universe's expansion. But the cosmological constant is just one of many possible explanations for dark energy. Another idea is that dark energy could be a dynamic field, something that changes over time and space. This concept, known as quintessence, suggests that dark energy is not a constant, but a fluid-like entity that ebbs and flows across the cosmos. This would mean that the universe's expansion rate could change in the future, potentially slowing down or even reversing. Yet another possibility is that our understanding of gravity itself might need to be revised. Some theories suggest that gravity could behave differently on very large scales, and that dark energy might be a manifestation of these new gravitational effects. These ideas are still in the realm of speculation, and each presents its own set of challenges and unanswered questions. What makes dark energy so frustrating and fascinating for scientists is its lack of direct evidence. Unlike other cosmic phenomena, which can be observed and measured, dark energy has only been inferred from its effects on the expansion of the universe. It's like trying to solve a mystery with only the faintest of clues, piecing together a picture of something that remains stubbornly out of reach. This has led to a wide range of theories and models, each trying to explain what dark energy might be and how it works. But so far, none of these theories has provided a definitive answer. The enigma of dark energy is not just a scientific puzzle, it's a profound philosophical challenge. It forces us to confront the limitations of our knowledge and the possibility that there are aspects of the universe that are fundamentally beyond our understanding. It's a humbling reminder that, despite all our technological advances and scientific achievements, we are still in the early stages of understanding the cosmos. The discovery of dark energy has opened a new chapter in our exploration of the universe, one that may require us to rethink everything we thought we knew. In many ways, dark energy is the ultimate cosmic mystery, a force that operates on scales that are difficult to comprehend. It's a reminder that the universe is far stranger and more complex than we can imagine, a place where the rules of physics as we know them may not apply. It challenges us to keep searching, to keep asking questions, and to keep pushing the boundaries of our understanding. Dark energy is a puzzle that may not be solved in our lifetime or ever, but it's a mystery that drives us to explore, to discover, and to seek out the unknown. And in that sense, it is one of the most compelling and exciting challenges in all of science. The universe has always been a place of immense wonder, a vast expanse that has captivated the minds of scientists, philosophers, and dreamers alike. For centuries, we have tried to unravel its mysteries, seeking to understand the forces that shape its destiny. One of the most profound revelations in this quest for knowledge came not from what we saw, but from what we didn't expect to see. It was a discovery that shook the very foundations of cosmology, challenging our most basic understanding of the cosmos and the forces that govern it. The universe, we found, was not just expanding, it was accelerating. For much of human history, the universe was thought to be static, unchanging, a fixed backdrop against which the drama of existence played out. Even as we began to understand that the stars were distant suns, that the Earth was not the center of the universe, and that galaxies existed far beyond our own, the idea of a static cosmos persisted. It was only in the early 20th century, with Edwin Hubble's observations, that we began to understand that the universe was expanding. Galaxies, it seemed, were moving away from us, and the farther away they were, the faster they were receding. This expansion was a direct consequence of the Big Bang, the moment of creation that set the cosmos in motion. It was a discovery that changed everything, revealing a dynamic universe in a state of constant flux. But even as this new understanding of the universe took hold, there was an assumption that governed our thinking: gravity. Gravity, the force that pulls objects together, was seen as the great unifier, the force that would eventually slow the expansion of the universe. It made sense, after all. The universe, born in a moment of explosive expansion, would gradually feel the pull of gravity. Galaxies would slow their outward rush, their speed decreasing as gravity worked to counteract the momentum of the Big Bang. Perhaps some thought the expansion would eventually stop altogether, and the universe would begin to contract, leading to a big crunch. Others envisioned a universe that would continue expanding forever, but at an ever-decreasing rate, asymptotically approaching a standstill. These were the scenarios that made sense, that fit within our understanding of the cosmos. But in 1998, something extraordinary happened. Two independent teams of astronomers, studying distant supernovae, exploding stars that serve as cosmic mile markers, found something that defied all expectations. Instead of slowing down, the expansion of the universe was speeding up. The universe, it seemed, was not coasting to a stop, but accelerating, like a car that had suddenly found a new burst of speed. It was as if, after billions of years, the universe had decided to pick up the pace. This was a discovery that was as shocking as it was profound. It wasn't just that the universe was expanding faster. It was expanding faster in a way that contradicted the very laws of physics as we understood them. The implications of this discovery were staggering. If the universe was accelerating, it meant that there was something out there, something powerful enough to overcome the pull of gravity, pushing galaxies apart with an invisible force. This was not just a small anomaly. It was a fundamental shift in our understanding of the cosmos. Gravity, the force that had been the cornerstone of physics since Newton, was no longer the dominant player on the cosmic stage. Instead, there was a new force, something that we had never seen or felt, but that was clearly at work on the grandest of scales. This force was given a name, dark energy, but the name was merely a placeholder for something we couldn't explain. To understand just how unexpected this discovery was, it's important to consider the mindset of scientists before 1998. The universe was seen as a battle between two forces: the initial energy of the Big Bang, driving expansion, and gravity, pulling everything back together. This was a neat and tidy model, one that fit with the laws of physics as we knew them. It was a universe that made sense, a universe where the rules were clear. The idea that a third force, something entirely unknown, could enter the picture and change everything was almost unthinkable. And yet, that's exactly what happened. The discovery of the accelerating universe forced scientists to rethink their most basic assumptions about the cosmos. Gravity, it turned out, was not the only force at play. There was something else, something that didn't fit into any existing theory. This was a profound challenge to the field of cosmology, one that has led to decades of research and speculation. What could be causing this acceleration? Was it some new form of energy? Was our understanding of gravity itself flawed? These were questions that no one had answers to, and they remain unanswered to this day. The idea that the universe is accelerating is counterintuitive in the extreme. Everything we know about gravity tells us that it should be pulling things together, not pushing them apart. And yet, that's exactly what we see. The farther away we look, the faster galaxies are receding from us, as if the universe is being stretched by some unseen hand. This is not just a small discrepancy. It's a fundamental challenge to our understanding of the cosmos. It suggests that there is something about the universe that we don't understand, something that lies beyond the reach of our current theories. One of the most puzzling aspects of this acceleration is that it doesn't seem to have any direct cause. When we look at the universe, we see galaxies, stars, and planets, all bound together by gravity. But we don't see anything that could be causing this acceleration. Dark energy, as it's called, doesn't interact with light, so we can't see it. It doesn't seem to clump together like matter, so we can't detect it through gravitational effects. It's as if the universe is filled with an invisible fluid, something that exerts pressure on the cosmos, driving its expansion ever faster. But what this fluid is, or how it works, remains a mystery. The discovery of the accelerating universe has opened up a whole new field of inquiry in cosmology. Scientists are now trying to understand what dark energy is, how it works, and what it means for the future of the universe. Some theories suggest that dark energy is a property of space itself, an inherent energy that increases as space expands. Others propose that it could be a new kind of field, something that changes over time in space. Still, others suggest that our understanding of gravity might need to be revised, that the laws of physics as we know them might not apply on the largest scales. Each of these ideas is speculative, and each presents its own challenges. But what makes this discovery so profound is not just the mystery of dark energy itself, but what it means for the fate of the universe. If the universe is accelerating, then its ultimate destiny might be very different from what we once imagined. Instead of slowing down and contracting, the universe could continue expanding forever, growing colder and darker as galaxies drift farther apart. In this scenario, known as the Big Freeze, the universe would eventually become a cold, empty place, with stars burning out and galaxies becoming isolated islands in an ever-expanding void. Alternatively, the acceleration could increase to the point where the universe tears itself apart in a scenario known as the Big Rip. In this case, Not just galaxies, but stars, planets, and even atoms would be torn apart by the relentless expansion. These are not just scientific speculations. They are deeply unsettling ideas that challenge our understanding of the universe and our place within it. The idea that the universe could end not in fire, but in ice, or that it could tear itself apart, is a stark reminder of how little we truly understand about the cosmos. It forces us to confront the limits of our knowledge and the possibility that the universe is far stranger and more complex than we ever imagined. In the end, the discovery of the accelerating universe is a story of humility and wonder. It's a reminder that, despite all our advances in science and technology, we are still just beginning to understand the cosmos. The universe is a place of immense mystery, a place where the rules can change, and where new discoveries can upend everything we thought we knew. The accelerating expansion of the universe is one of the greatest mysteries of modern science, a puzzle that challenges our understanding and drives us to keep exploring. It's a testament to the power of science to reveal the unknown, and to the boundless curiosity that drives us to seek out the mysteries of the cosmos. The universe is a vast and intricate web of matter, energy, and forces, a cosmic tapestry that stretches across the infinite expanse of space. For centuries, our understanding of the universe was shaped by what we could see: the stars twinkling in the night sky, the planets orbiting their suns, and the galaxies swirling like cosmic pinwheels in the darkness. These celestial objects, composed of ordinary matter, seemed to be the primary actors on the cosmic stage. They were the things we could touch, see, and measure, the tangible stuff of the universe. But as our understanding of the cosmos has deepened, we've come to realize that what we see is only a tiny fraction of what actually exists. Beneath the visible universe lies a much larger, stranger world. A world dominated by something we can't see, something that defies our understanding and challenges our perceptions of reality. This unseen force, known as dark energy, is not just a curious anomaly. It's the most dominant force in the universe, far outweighing the matter that makes up stars, planets, and galaxies. And that, perhaps, is one of the most difficult concepts to grasp. When we look out into the universe, what we see, stars, galaxies, nebulae, and all the celestial objects that populate the cosmos, constitutes only a small fraction of the universe's total composition. This ordinary matter, the stuff that makes up everything we know and experience, is less than 5% of the universe. It's a humbling realization, one that forces us to confront the limits of our understanding. Even dark matter, which doesn't emit or absorb light, but exerts gravitational influence, accounts for only about 27% of the universe. But dark energy? Dark energy makes up a staggering 68% of the universe. It's not just a small piece of the puzzle. It's the puzzle itself, the overwhelming force that governs the universe's fate. To say that dark energy is dominant is an understatement. It's as if the universe is composed of two worlds: the visible world of stars and galaxies, and an invisible world of dark energy that permeates every corner of space. The idea that this unseen force controls the universe's destiny is difficult to grasp, not just because we can't see it, but because it defies our most basic understanding of how the universe works. In the world of the visible, gravity is king. It's the force that pulls matter together, that governs the orbits of planets, the formation of stars, and the structure of galaxies. But in the world of the unseen, dark energy is the ruler, pushing everything apart, driving the universe's expansion ever faster. What makes dark energy so perplexing is not just its dominance, but its nature. Unlike matter, which clumps together to form galaxies, stars, and planets, dark energy doesn't seem to gather or interact in any way that we can detect. It's not something that can be observed directly. Instead, it reveals itself only through its effects on the universe. It's as if the universe is filled with an invisible, intangible force that influences everything but can't be pinned down or measured in the usual ways. This makes dark energy an enigma, a force that exists outside the realm of our everyday experience, and yet is the most significant component of the cosmos. The realization that dark energy is far more prevalent than ordinary matter forces us to reconsider our place in the universe. For so long, we've thought of the universe as a place dominated by the visible, by the stars and galaxies that light up the night sky. But the truth is far stranger. The universe is not a place dominated by the seen, but by the unseen. Dark energy is everywhere, an invisible force that fills the universe, influencing its evolution on the grandest of scales. It's not just that dark energy is more abundant than matter, it's that it's in control. It's the force that will determine the ultimate fate of the universe, driving its expansion, shaping its future, and possibly leading to its end. What's perhaps most difficult to grasp about dark energy's dominance is its implications. If dark energy is the most significant component of the universe, then it's not the stars and galaxies that will dictate the universe's future, but this unseen force. The galaxies we see, the stars that shine, and the planets that orbit them are all subject to the influence of dark energy. They are not the masters of their own fate. They are at the mercy of a force that we barely understand. And that's a profoundly unsettling thought. It suggests that the universe is not as it appears, that the visible world is only a small part of a much larger, much stranger reality. The idea that dark energy is in control forces us to confront the limits of our knowledge. For centuries, we've built our understanding of the universe on what we can observe and measure. But dark energy exists outside those boundaries. It's a force that we can't see or measure directly, and yet it's the most important force in the universe. It challenges us to think beyond the visible, to consider that there are aspects of the universe that are fundamentally beyond our current understanding. It's a humbling realization, one that forces us to reconsider everything we thought we knew about the cosmos. Dark energy's dominance also raises profound questions about the nature of reality itself. If the universe is mostly made up of something we can't see or detect, what does that say about our understanding of the cosmos? What else might be out there beyond our ability to perceive? Dark energy suggests that the universe is a far stranger place than we ever imagined, a place where the rules we take for granted don't always apply. It's a reminder that the universe is not just a collection of stars and galaxies, but a vast, mysterious entity that operates on levels we can barely comprehend. As we continue to study dark energy, we're forced to confront the possibility that our current theories of the universe are incomplete. Dark energy doesn't fit neatly into our existing models of physics. It's a puzzle piece that doesn't quite match the rest of the picture. This has led scientists to explore new ideas, new theories that might explain the nature of dark energy and its role in the universe. Some of these theories are radical, suggesting that our understanding of gravity itself might be flawed. Others propose that dark energy could be a new kind of field, something that interacts with space in ways we don't yet understand. But whatever the true nature of dark energy, one thing is clear. It's the key to understanding the universe's future. The dominance of dark energy also forces us to confront the possibility that the universe's fate might be very different from what we once imagined. If dark energy continues to drive the universe's expansion, then the galaxies, stars, and planets that make up the visible universe could become increasingly isolated, drifting apart in an ever-expanding void. The universe could grow colder, darker, and more desolate as time goes on, with the visible world gradually fading into nothingness. It's a bleak vision of the future, one that contrasts sharply with the vibrant, dynamic universe we see today. But it's a vision that's consistent with the dominance of dark energy, a force that pushes the universe apart rather than pulling it together. In the end, the dominance of dark energy is a reminder of how little we truly understand about the universe. It's a force that challenges our assumptions, that forces us to confront the limits of our knowledge, and that suggests the universe is far more complex and mysterious than we ever imagined. Dark energy is not just a scientific curiosity. It's the most significant force in the universe, the key to understanding the cosmos and its ultimate fate. And as we continue to explore this mysterious force, we're reminded that the universe is not just a place of light and matter, but a place of darkness and mystery, where the unseen holds sway over the seen, and where the forces that shape the cosmos are far stranger than we ever imagined. The discovery of dark energy has been nothing short of a seismic shift in our understanding of the universe, a revelation that has sent ripples through the very foundations of physics. For centuries, the laws of physics have been our guide to understanding the cosmos, providing us with a framework that explains the behavior of everything from the smallest particles to the largest galaxies. These laws, rooted in the theories of gravity, electromagnetism, quantum mechanics, and relativity, have allowed us to unlock many of the universe's secrets. But with dark energy, we've encountered something that doesn't fit neatly into this well-established framework, something that challenges the very concepts that have long been considered fundamental. At the heart of this challenge lies gravity, the force that governs the motion of planets, the formation of stars, and the structure of galaxies. Gravity, as described by Einstein's theory of general relativity, is the curvature of space and time caused by mass and energy. It's a force that pulls objects together, a force that has shaped the universe from the moment of its creation. But dark energy defies this notion. Instead of pulling things together, dark energy seems to be pushing them apart, driving the accelerated expansion of the universe. This discovery was both unexpected and profoundly unsettling, for it suggests that our understanding of gravity might be incomplete. For decades, physicists believed that the expansion of the universe, which began with the Big Bang, would gradually slow down over time due to the pull of gravity. The idea was that the gravitational attraction between galaxies and other matter would cause the expansion to decelerate, perhaps even leading to a future where the universe might contract again in a big crunch. This was a logical extension of our understanding of gravity, a force that always attracts, that always pulls. But in the late 20th century, observations of distant supernovae revealed something startling. The expansion of the universe wasn't slowing down at all. It was speeding up. This acceleration could only be explained by the presence of some mysterious force that was acting in opposition to gravity, something that was driving galaxies apart rather than pulling them together. This force was dubbed dark energy, and its discovery marked the beginning of a new era in cosmology, one where the established laws of physics were called into question. The existence of dark energy has forced scientists to reconsider the nature of space and time itself. In Einstein's theory of general relativity, space and time are intertwined in a four-dimensional fabric that is shaped by the presence of mass and energy. This fabric can stretch, warp, and bend, but the introduction of dark energy suggests that space and time might be even more complex than we thought. If dark energy is causing the accelerated expansion of the universe, it means that space itself is expanding, stretching outwards in a way that defies our traditional understanding of gravity. This has led to a re-examination of the very concept of a cosmological constant, a term that Einstein originally introduced into his equations of general relativity to allow for a static universe. When it was later discovered that the universe was expanding, Einstein discarded the cosmological constant, calling it his greatest blunder. But with the discovery of dark energy, the cosmological constant has made a comeback. It's now thought that this constant might be a representation of dark energy, a term that accounts for the accelerated expansion of the universe. The idea that Einstein's blunder might actually be the key to understanding dark energy is both ironic and deeply thought-provoking, forcing us to consider that the universe might be even stranger than Einstein himself could have imagined. But the challenge of dark energy goes beyond gravity and the cosmological constant. It extends to our understanding of quantum mechanics, the theory that describes the behavior of particles on the smallest scales. Quantum mechanics is a theory that has been incredibly successful in explaining the behavior of atoms, molecules, and subatomic particles. But when it comes to dark energy, it falls short. One of the most perplexing questions in physics is why the amount of dark energy in the universe is so small compared to what quantum mechanics would predict. If quantum mechanics is correct, the energy of empty space, what physicists call the vacuum energy, should be enormous, far greater than what we observe. But the actual amount of dark energy in the universe is incredibly small, a tiny fraction of what quantum theory would suggest. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved problems in physics, a puzzle that has confounded scientists for decades. The challenge of dark energy has also led to the exploration of new, speculative theories that go beyond our current understanding of physics. Some physicists have proposed that dark energy might be a manifestation of a new field, something akin to the electromagnetic field that governs the behavior of charged particles. This hypothetical field, sometimes referred to as quintessence, would vary in strength over time and space, providing a possible explanation for the accelerating expansion of the universe. But quintessence is just one of many ideas, and it remains highly speculative, with no direct evidence to support it. Other theories suggest that our understanding of gravity itself might need to be revised. Modified gravity theories propose that the laws of gravity might change on very large scales, where dark energy becomes significant. These theories challenge the very foundation of general relativity, suggesting that Einstein's equations might need to be modified to account for the effects of dark energy. But like quintessence, these ideas remain speculative, and there's no consensus among scientists about which, if any, of these theories might be correct. The implications of dark energy extend even further, challenging our understanding of the universe's ultimate fate. If dark energy continues to drive the accelerated expansion of the universe, it could lead to a future where galaxies drift apart, stars burn out, and the universe becomes a cold, dark, and desolate place, a scenario known as the Big Freeze. Some theories even suggest that the expansion could eventually tear everything apart, including galaxies, stars, planets, and even atoms, in a cataclysmic event known as the Big Rip. These possibilities are difficult to comprehend, not just because they are so far removed from our everyday experience, but because they challenge the very concepts of space, time, and matter. The discovery of dark energy has also led to philosophical questions about the nature of the universe and our place in it. If the universe is dominated by a force that we don't understand, a force that doesn't fit neatly into our existing theories of physics, what does that say about our ability to comprehend the cosmos? Are there aspects of the universe that are fundamentally beyond our understanding? Dark energy suggests that the universe might be far more complex and mysterious than we ever imagined, a place where the rules we take for granted don't always apply. It's a reminder that science is not just about answering questions, but about discovering new ones, about pushing the boundaries of what we know and venturing into the unknown. In many ways, the challenge of dark energy is a testament to the power and limitations of science. It's a force that has forced us to rethink our most fundamental concepts, to question the very nature of reality itself. It's a reminder that the universe is a place of wonder and mystery, a place where the more we learn, the more we realize how much we don't know. Dark energy is not just a puzzle for physicists to solve. It's a window into the unknown, a force that challenges us to think beyond the limits of our current understanding and to explore the deeper mysteries of the cosmos. As we continue to study dark energy, we're reminded that science is a journey, not a destination. It's a journey that takes us to the farthest reaches of the universe, to the very edge of our understanding and beyond. Dark energy is a challenge, a force that defies our expectations and pushes us to think in new and creative ways. But it's also an opportunity, a chance to explore the deepest mysteries of the universe and to uncover the secrets that lie hidden in the darkness. And in that sense, the discovery of dark energy is not just a challenge, but a celebration of the human spirit, a testament to our unending curiosity and our relentless pursuit of knowledge. Imagine a night sky where the stars slowly fade, one by one, until the vastness of space becomes nothing but a cold, empty void. This is not just a poetic vision of the end of days, but a real possibility when we consider the role of dark energy in shaping the ultimate fate of our universe. It's a chilling thought, one that can send shivers down your spine. The universe, which has been expanding ever since the Big Bang, might one day end up as a barren, lifeless expanse, stretching into infinity with no trace of the vibrant cosmos we know today. The story of dark energy is a tale of cosmic mystery. Discovered in the late 20th century, it's an enigma that refuses to be fully understood. Unlike anything we can see, touch, or measure directly, Dark energy is a force that permeates all of space, driving the universe to expand at an ever-accelerating rate. It's as if the cosmos itself is being pushed apart by an invisible hand, one that doesn't care about the galaxies, stars, or planets that it affects. This invisible force makes up about 68% of the universe's total energy, dwarfing everything else. Yet its nature remains elusive. One of the most unsettling implications of dark energy is its potential to dictate the universe's final destiny. There are a few theories about how this might play out, and none of them are particularly comforting. The most widely discussed scenarios are the Big Freeze and the Big Rip, each offering a different, yet equally bleak, vision of the future. The Big Freeze scenario suggests a universe that keeps expanding forever. As dark energy continues to push galaxies apart, the universe will gradually become colder and darker. Stars will burn out, galaxies will drift away from each other, and the once bright cosmos will be left in darkness. In this scenario, the universe doesn't end in a fiery explosion, but rather in a slow, quiet fade to black. Over unimaginable timescales, even black holes, the last remaining objects in the universe, will evaporate into nothingness through a process known as Hawking radiation. What's left after that? Just a thin, cold soup of particles, drifting through an ever-expanding void. The Big Rip, on the other hand, offers a more violent end. If dark energy's influence increases over time, it could eventually overcome all other forces, even gravity. This would mean that not only galaxies and stars would be torn apart, but also planets, atoms, and the very fabric of space-time itself. Imagine a universe where the fundamental bonds that hold matter together are ripped apart. In the final moments of a Big Rip scenario, even subatomic particles would be shredded, leaving behind a universe devoid of any structure whatsoever, a literal tearing apart of reality itself. These scenarios challenge our understanding of existence. We're used to thinking of the universe as a stable place, one governed by rules we can learn and understand. But dark energy forces us to confront the idea that the universe is more unpredictable and stranger than we ever imagined. The thought that the universe could end, not with a bang, but with a whimper or a violent tear, raises deep philosophical questions about the nature of reality and our place within it. There's also a sense of helplessness that comes with contemplating these possibilities. Dark energy isn't something we can control or influence. It's a fundamental force of nature that operates on the largest scales imaginable. Its effects are so vast and so all-encompassing that they render us, and everything we know, insignificant in comparison. It's like being on a ship lost at sea, with no control over the currents that will eventually decide your fate. All we can do is observe, theorize, and wonder about what the future holds. As we look to the stars and try to understand the cosmos, dark energy serves as a reminder of the limits of human knowledge. For all our advances in science and technology, there are still fundamental aspects of the universe that elude our understanding. The fact that something as crucial as dark energy could remain a mystery speaks to the humbling nature of cosmic inquiry. It forces us to confront the possibility that there are some things we might never fully understand, and that the universe is far stranger and more complex than we can imagine. But while dark energy raises unsettling questions, it also invites us to push the boundaries of our knowledge. The very fact that we can contemplate these ideas is a testament to the power of human curiosity and the drive to understand the world around us. Scientists around the world are working to unlock the secrets of dark energy, developing new theories and conducting experiments that might one day provide answers. Whether it's through the study of distant supernovae, the mapping of the cosmic microwave background, or the exploration of alternative theories of gravity, the quest to understand dark energy is one of the most exciting and challenging endeavors in modern science. In the end, the story of dark energy is still being written. We don't know how it will end, or even if we'll ever find the answers we're looking for. But the journey itself is a reminder of what it means to be human, to look up at the night sky, to wonder about the nature of the universe, and to seek answers to the most profound questions about existence. These are the qualities that define us. Dark energy may be a mystery, but it's also a doorway to a deeper understanding of the cosmos and our place within it. So, as you ponder the fate of the universe, consider this. The very act of asking these questions is part of what makes us special. Whether the universe ends in a big freeze, a big rip, or something else entirely, our curiosity and our drive to understand will continue to light the way, even as the stars themselves begin to fade. In the vast, dark expanse of the universe, there are secrets hidden so deeply that they seem almost untouchable, like whispers in the wind that you can sense but never quite hear. Dark energy is one of those secrets, an invisible force that shapes the cosmos, yet eludes our grasp in a way that leaves even the most brilliant minds scratching their heads. To understand the mystery of dark energy, you first have to grapple with the idea that we've never actually seen it, measured it, or directly observed its presence. Instead, we know it's there, like a ghostly presence, only through the strange and unexpected ways it makes its influence felt across the universe. Think about the way we first began to understand the cosmos. We started by observing what we could see, the stars, the planets, the way they move. Newton's laws of motion and gravity explained so much of the universe, showing us that these heavenly bodies dance in a predictable way, following rules that we could understand. Then, as our technology advanced, we began to see more. Telescopes revealed galaxies far beyond our own, and we learned that the universe is far bigger and more complex than we ever imagined. But even as our understanding grew, there were things that didn't add up. For instance, when astronomers looked at galaxies, they noticed something strange. The stars at the edges of these galaxies were moving much faster than they should be, based on the visible matter alone. It was as if there was some invisible mass, something we couldn't see, exerting a gravitational pull that kept these stars from flying off into space. This was our first hint of dark matter, an unseen substance that makes up about 27% of the universe. While we still don't know exactly what dark matter is, we've gathered plenty of indirect evidence of its existence through its gravitational effects. Dark energy, however, is an entirely different beast. Unlike dark matter, it doesn't reveal itself through gravity. Instead, its presence is inferred from something even more astonishing: the expansion of the universe. For a long time, scientists believed that the universe, after the Big Bang, was slowly decelerating in its expansion. After all, gravity should be pulling everything back together, right? But then came a shocking discovery in the late 1990s. Observations of distant supernovae showed that not only is the universe still expanding, but this expansion is actually accelerating. This was a revelation that turned everything we thought we knew about the cosmos on its head. This accelerating expansion is like a puzzle piece that doesn't fit with the others. It suggests that there is something out there, something powerful, that's driving the universe to expand faster and faster over time. And that's something we now call dark energy. But here's the catch. Despite its monumental influence, dark energy is elusive. Unlike dark matter, which we can infer from the way it bends light and affects the motion of stars, dark energy has left us with almost nothing to hold on to. We know it's there because the universe is expanding faster than it should be, but that's about all we know. It's like standing in the middle of a deserted town and seeing the windows of a house mysteriously open and close by themselves. You know something is causing it, but you can't see what's doing it. This lack of direct evidence makes dark energy one of the most puzzling phenomena in modern science. Scientists have proposed various theories to explain what dark energy might be. Some think it could be a new type of energy field that permeates all of space, a sort of quintessence that changes over time. Others suggest it could be a property of space itself, a kind of energy that comes from the very fabric of the universe. There's even the possibility that our understanding of gravity is incomplete, and that dark energy is a sign that we need to rethink one of the most fundamental forces in the universe. Yet, despite these theories, we're still in the dark, literally and figuratively. We can't directly observe dark energy in the way we can observe stars, planets, or even dark matter. We can't detect it with our instruments, measure it in a laboratory, or see it in a telescope. All we have are the effects it leaves behind. The accelerating expansion of the universe, like ripples in a pond after a stone has been thrown in, long after the stone has sunk out of sight. This elusiveness is what makes dark energy so profoundly mysterious. It's as if the universe is hiding a part of itself from us, keeping its deepest secrets just out of reach. Every time we think we're getting closer to understanding the cosmos, dark energy reminds us that there is so much we still don't know. It's humbling, in a way, to realize that we are living in a universe where such a vast and powerful force can exist, and yet remain so completely hidden from us. And this mystery isn't just a scientific curiosity. It has profound implications for our understanding of the universe. If dark energy exists, and if it continues to drive the expansion of the universe at an accelerating rate, what does that mean for the future? Will the universe continue to expand forever, growing colder and darker as galaxies drift apart into the void? Or is there something else at play, something we haven't yet imagined, that could change the fate of the cosmos? These questions, sparked by the elusive nature of dark energy, are what drives scientists to keep searching, to keep looking for that one piece of evidence that might finally unlock the mystery. But for now, dark energy remains just out of reach, a cosmic ghost that haunts our understanding of the universe, challenging us to keep exploring, to keep asking questions, and to never stop seeking the truth. In the end, dark energy is a reminder of how much we still have to learn, of how the universe is full of surprises waiting to be discovered. It's a testament to the fact that even in the 21st century, with all our technology and knowledge, there are still mysteries out there that we can barely begin to comprehend. And that's what makes dark energy so fascinating, because it's not just about what we know, but about the endless possibilities of what we might yet discover. In the annals of scientific history, there are few moments as poignant and humbling as when a brilliant mind like Albert Einstein declares something to be a mistake. The cosmological constant, a term Einstein introduced into his equations of general relativity, is one such case. It's a story of intellectual humility, scientific exploration, and the surprising twists that the pursuit of truth can take. Yet, what makes this tale even more intriguing is the possibility that Einstein's so-called blunder might not have been a mistake at all. In fact, it could be one of the most profound and accurate descriptions of the universe we've ever stumbled upon. To understand this, we have to go back to the early 20th century, a time when Einstein was revolutionizing our understanding of space, time, and gravity. His theory of general relativity, published in 1915, was a groundbreaking achievement. It described how massive objects like stars and planets bend the fabric of space-time, creating the force we experience as gravity. This theory elegantly explained the motion of planets, the bending of light around stars, and even predicted the existence of black holes. However, there was one problem. The universe it described wasn't static. At the time, the prevailing belief was that the universe was unchanging, a fixed stage where the cosmic drama played out. But Einstein's equations suggested otherwise. They indicated that space itself could expand or contract, that the universe was dynamic. This was unsettling because it clashed with the philosophical and scientific views of the day. To reconcile his equations with the idea of a static universe, Einstein introduced a new term, the cosmological constant. This was a mathematical fix, a kind of anti-gravity force that would counteract the pull of gravity and keep the universe in balance, neither expanding nor contracting. For a while, this seemed to work. The cosmological constant made the equations fit the prevailing idea of a static universe, and everything seemed to be in order. But then, in the 1920s, astronomer Edwin Hubble made a discovery that would change everything. By observing distant galaxies, Hubble found that they were all moving away from us, suggesting that the universe was expanding. This was the first observational evidence that the universe was not static, but dynamic, expanding over time. Einstein was reportedly dismayed by this revelation. The cosmological constant, which he had introduced to force his equations to describe a static universe, now seemed unnecessary. He called it his greatest blunder, a mistake that had clouded his otherwise impeccable theory. In the wake of Hubble's discovery, the cosmological constant was largely abandoned, a relic of a time when the universe was thought to be still and eternal. Fast forward to the late 20th century, and the story takes a surprising turn. In the 1990s, two independent teams of astronomers made a discovery that would shake the foundations of cosmology once again. By studying distant supernovae, they found that not only was the universe expanding, but it was doing so at an accelerating rate. This was completely unexpected. If gravity was the only force at play, the expansion should be slowing down as galaxies pulled on each other. Instead, something seemed to be pushing them apart, causing the expansion to speed up. This mysterious force was dubbed dark energy, and it reignited interest in the cosmological constant. Suddenly, Einstein's blunder didn't seem like a mistake at all. The cosmological constant could explain this acceleration, serving as a kind of repulsive force that drives the expansion of the universe. It was as if a piece of a puzzle, long discarded, was found to fit perfectly in the picture we were now seeing. But this wasn't just about Einstein being vindicated. The revival of the cosmological constant opened up profound questions about the nature of the universe and our place in it. If the cosmological constant is indeed the correct description of dark energy, it suggests that the fabric of space itself has an inherent energy, a kind of pressure that pushes outward, driving the acceleration of the universe. This idea is both elegant and unsettling. It means that the expansion of the universe isn't just a result of the initial conditions of the Big Bang, but is being driven by a force that is woven into the very nature of space-time. What makes this so surprising is the way it challenges our understanding of reality. The cosmological constant is incredibly small, yet its effects are seen on the largest scales imaginable, influencing the entire universe. It's as if a tiny, almost imperceptible force is shaping the destiny of the cosmos. And this force isn't something we can directly observe or measure in a lab. It's inferred from the way the universe behaves on grand scales. This is where the story of the cosmological constant becomes truly thought-provoking. Imagine, for a moment, the implications of this tiny constant. If it's truly constant, unchanging over time, it suggests that the universe will continue to expand forever, growing colder and more diffuse as galaxies drift apart into the void. This could lead to a future known as the Big Freeze, where the universe becomes a cold, dark, and empty place. Alternatively, if the cosmological constant changes over time, it could lead to even more exotic fates for the universe, such as the Big Rip, where the expansion becomes so intense that it tears apart galaxies, stars, and eventually even atoms themselves. These scenarios are difficult to comprehend, not just because they are so far removed from our everyday experience, but because they force us to confront the limits of our understanding. The cosmological constant, once a simple term added to balance equations, has become a window into the deepest mysteries of the cosmos. It challenges us to rethink the nature of space, time, and energy, and to consider possibilities that stretch the imagination. But perhaps what's most intriguing about the cosmological constant is the way it reflects the twists and turns of scientific discovery. Einstein's introduction of the cosmological constant was an attempt to force the universe into a mold that matched the prevailing ideas of the time. When those ideas changed, the constant was dismissed, seemingly an artifact of a bygone era. Yet, as our understanding evolved, the cosmological constant re-emerged, not as a mistake, but as a profound insight into the nature of the universe. This story is a reminder that science is not a straight path to the truth, but a journey full of surprises, wrong turns, and unexpected revelations. It shows us that even the greatest minds can make mistakes, and that those mistakes can sometimes lead to deeper truths. The cosmological constant, once dismissed as a blunder, might just be one of the most important concepts in our understanding of the universe, a testament to the complexity and beauty of the cosmos we live in. In the end, the cosmological constant's comeback is more than just a vindication of Einstein's genius. It's a story about the ever-evolving nature of scientific knowledge, the way our understanding of the universe is constantly being challenged and refined. It's a reminder that in the quest to understand the cosmos, even the most brilliant theories can be revised, reinterpreted, and rediscovered in ways that we never expected. And in that sense, the cosmological constant is not just a term in an equation. It's a symbol of the enduring mystery and wonder of the universe itself. Imagine stepping into a room filled with strange and intricate machinery, the kind that hums with energy and purpose, but whose inner workings are a complete mystery. The gears turn, lights flash, and the entire system seems to be alive with an intelligence of its own. You can see it moving, feel its power, but you can't quite grasp how it all fits together. This is what it feels like to explore the theories surrounding dark energy. Ideas that are complex, speculative, and challenge our very understanding of the universe. When astronomers discovered that the universe's expansion was accelerating, it threw the scientific community into a frenzy. The familiar models of the cosmos, which had served us well for so long, suddenly seemed incomplete. There was something out there, an unknown force, driving galaxies apart faster and faster. But what was it? Theories began to emerge, each more intricate and challenging than the last, as scientists tried to make sense of this cosmic puzzle. One of the first ideas to gain traction was the theory of quintessence. Unlike the cosmological constant, which posits a uniform, unchanging force, quintessence suggests that dark energy is a dynamic field, something that evolves over time. Imagine it as a kind of energy fluid that permeates the universe, but with properties that change depending on where and when you observe it. This is not a simple notion. Quintessence doesn't fit neatly into the boxes of classical physics. It requires a rethinking of how we understand energy, space, and time. Unlike the cosmological constant, which Einstein envisioned as a static, ever-present force, quintessence is alive with potential, fluctuating and adapting as the universe expands. This dynamic nature makes it a compelling candidate for dark energy, but it also adds layers of complexity to an already baffling mystery. To understand quintessence, imagine the universe as a landscape, with valleys, hills, and plateaus. In this analogy, quintessence would be like a rolling wave that moves across this landscape, sometimes accelerating, sometimes slowing down depending on the terrain. This idea challenges the classical view of the universe as a stable, predictable place. Instead, it suggests that the very fabric of the cosmos is in constant flux, influenced by an energy field that we are only beginning to understand. The implications of this are profound. If quintessence is correct, it means that dark energy could change over time, potentially altering the fate of the universe in ways we can scarcely imagine. But quintessence is just one of many theories. Another contender is modified gravity. This idea suggests that maybe it's not dark energy at all, but our understanding of gravity itself that is incomplete. Einstein's theory of general relativity has been incredibly successful in explaining the motions of planets, stars, and even the warping of space-time around massive objects. But what if, on the grandest scales of the universe, gravity behaves differently than we think? Modified gravity theories propose that the laws governing how matter interacts with space and time might change when you look at the universe as a whole. It's a bold idea, one that challenges the very foundation of physics. Modified gravity theories are like trying to rewrite the rulebook of the cosmos. They suggest that the equations that govern the movements of planets and galaxies might need an update, a kind of cosmic software patch to account for the mysterious acceleration we observe. These theories come in many flavors, from those that tweak Einstein's equations to others that propose entirely new forms of interaction between matter and space. What they all have in common is the idea that the force we call gravity might not be as simple as we once thought. Consider the implications of modified gravity. If our understanding of gravity is wrong, it means that everything we've built our physics on could be up for revision. The way we think about black holes, the curvature of space-time, even the formation of the universe itself could be different from what we currently believe. It's a humbling thought, one that forces us to consider that our view of the universe might be more limited than we ever imagined. Then there's the dark fluid theory, a concept as enigmatic as its name suggests. This theory proposes that dark energy and dark matter, two of the most mysterious components of the universe, are actually two sides of the same coin. Instead of being separate entities, dark energy and dark matter could be manifestations of a single, underlying substance, dark fluid. This idea is as ambitious as it is complex, merging the two great unknowns of modern cosmology into one. Dark fluid theory is like trying to solve two puzzles simultaneously, only to discover that the pieces of one puzzle fit perfectly into the other. If dark energy and dark matter are indeed the same thing, it would mean that the force driving the expansion of the universe and the mysterious substance holding galaxies together are part of a unified whole. But what exactly is this dark fluid? How does it interact with the visible matter we see around us? These questions are at the frontier of theoretical physics, pushing the boundaries of what we know and what we can imagine. The concept of dark fluid is mind-bending because it suggests that the distinctions we make between different forces and substances in the universe might be more of a limitation of our understanding than a reflection of reality. It's as if the universe is more interconnected than we ever thought, with dark energy and dark matter being just different expressions of a single, fundamental force. If this theory is correct, it would revolutionize our understanding of the cosmos, linking two of the biggest mysteries in modern science into a coherent, albeit deeply complex, framework. Each of these theories, quintessence, modified gravity, and dark fluid, offers a different lens through which to view the enigma of dark energy. They are not just scientific ideas. They are invitations to think differently about the universe, to question what we know, and to explore the boundaries of human knowledge. What makes these theories so fascinating is not just their complexity, but the way they challenge us to expand our understanding, to embrace the unknown, and to consider possibilities that are as strange as they are profound. But with these complex theories comes the realization that the more we learn, the more questions we uncover. Each theory, while offering potential answers, also opens new avenues of inquiry, new puzzles to solve. For instance, if quintessence is real, what causes this energy field to change over time? If gravity is modified, what does that mean for our understanding of space-time and the forces that govern the universe? If dark fluid is the answer, how do we reconcile this with what we know about the formation of galaxies and the large-scale structure of the cosmos? These are not easy questions, and the answers are far from clear. What is clear, however, is that we are at the edge of a new frontier in cosmology. Theories like quintessence, modified gravity, and dark fluid are more than just attempts to explain dark energy. They are steps toward a deeper, more nuanced understanding of the universe. They remind us that science is not just about finding answers, but about asking the right questions, about pushing the limits of what we know and exploring the vast unknown that lies beyond. In the end, these complex theories are a testament to the creativity and curiosity that drives scientific discovery. They show us that even in the face of the unknown, we have the tools, the imagination, and the determination to seek out answers. And as we continue to explore these ideas, we are reminded that the universe is a place of endless wonder, a cosmic mystery that beckons us to keep searching, to keep questioning, and to never stop being amazed by the world we live in. Picture yourself gazing up at a clear night sky, filled with countless stars. Each tiny speck of light represents a distant sun, many of which are part of vast galaxies like our own Milky Way. Now imagine zooming out from this scene, pulling back further and further until even the Milky Way itself becomes just a faint, swirling cloud among billions of others. As you continue to zoom out, the galaxies cluster together, forming massive structures like filaments and walls, separated by vast cosmic voids. But even at this unimaginable scale, you've only begun to scratch the surface of the universe's true grandeur. Beyond these galactic structures lies a force so pervasive, so all-encompassing, that it shapes the fate of the entire cosmos: dark energy. Dark energy operates on scales that stretch the limits of human comprehension. It's not something that exists in just one place or another, like a star or a planet. Instead, it's a force that permeates the entire universe, influencing everything from the motion of galaxies to the very structure of space-time. To truly grasp the impact of dark energy, you have to step back and consider the universe as a whole, an entity so vast and complex that it defies easy understanding. When we talk about cosmic scales, we're referring to distances and sizes that dwarf anything we experience in our daily lives. For example, light, which travels at the fastest speed possible in the universe, takes just over 8 minutes to reach us from the sun, which is a mere 93 million miles away. That's a comfortable distance by cosmic standards. But light from the nearest star, Proxima Centauri, takes over 4 years to reach us, traveling across trillions of miles of empty space. And that's just our cosmic backyard. Expand your view to the scale of galaxies, and the numbers become even more staggering. The Milky Way, with its hundreds of billions of stars, stretches about 100,000 light-years across. If you wanted to travel from one end of our galaxy to the other at the speed of light, it would take you 100 millennia. Yet, even our vast galaxy is just a tiny dot in the grand tapestry of the universe. Beyond it lie billions of other galaxies, each with their own billions or trillions of stars, spread across a universe that is estimated to be about 93 billion light-years in diameter. But what is truly mind-boggling is that dark energy doesn't just affect these massive structures. It shapes the universe on the largest scales imaginable. It is the force that drives the expansion of the universe, a process that began with the Big Bang and has been accelerating ever since. At first, it might seem counterintuitive. After all, gravity, the force that pulls matter together, should be slowing down the expansion of the universe, not speeding it up. Yet, observations of distant galaxies have shown that the universe isn't just expanding. It's doing so at an ever-increasing rate. This accelerating expansion is the hallmark of dark energy. Imagine throwing a ball into the air. Gravity will pull it back down, and eventually it will stop rising and fall back to the ground. But what if, instead of slowing down, the ball started speeding up as it ascended, rising faster and faster into the sky? That's the kind of effect dark energy has on the universe. It's as if something is pushing the galaxies apart, overcoming the pull of gravity and causing the universe to expand at an accelerating pace. The scale at which dark energy operates is difficult to fathom because it's not just a force that acts in one part of the universe or another. It's everywhere. It's not localized like gravity, which is strongest near massive objects like stars or black holes. Instead, dark energy is evenly distributed throughout the cosmos, exerting its influence on every part of space-time. It's this pervasive nature that makes dark energy so mysterious and so challenging to understand. To get a sense of the scale at which dark energy operates, consider this. The universe is vast, containing over 2 trillion galaxies, each filled with countless stars and planets. The observable universe, the portion of the cosmos we can see, stretches for about 46 billion light-years in every direction. And within this immense space, dark energy accounts for about 68% of the total energy content of the universe. That means more than 2/3 of the universe's energy is in the form of this invisible, all-encompassing force. What's even more astonishing is that dark energy doesn't just influence the universe today, it has been shaping its evolution for billions of years. In the early universe, dark energy was much less significant. Back then, gravity dominated, pulling matter together to form the first stars and galaxies. But as the universe expanded and matter became more spread out, the influence of dark energy grew. About 5 billion years ago, dark energy's repulsive force began to overpower gravity's pull, leading to the accelerated expansion we observe today. This transition from a universe dominated by gravity to one dominated by dark energy is a turning point in cosmic history. It's as if the universe has shifted gears, moving from a period of formation and consolidation to one of expansion and dispersion. And this change has profound implications for the future of the cosmos. If dark energy continues to drive the expansion of the universe, it could lead to a future where galaxies drift further and further apart, eventually becoming so isolated that they disappear from each other's view. This scenario, known as the Big Freeze, envisions a universe that becomes increasingly cold, dark, and empty as time goes on. Stars will eventually burn out, leaving behind cold remnants like white dwarfs and black holes. Galaxies will grow dim and fade into the vastness of space. In the end, the universe could become a cold, dark void, with only the faintest remnants of the once vibrant cosmos remaining. But the sheer scale of dark energy's impact doesn't end there. Some theories suggest that dark energy might not be constant. It could change over time, growing stronger or weaker. If dark energy were to grow stronger, it could lead to a more dramatic end for the universe, known as the Big Rip. In this scenario, dark energy would become so powerful that it would overcome not just the gravitational pull between galaxies, but the forces holding galaxies together, tearing apart stars, planets, and even atoms themselves. The universe would literally be ripped apart, leaving behind nothing but a featureless void. These scenarios are difficult to wrap our minds around because they operate on such vast scales, both in space and time. The idea that an invisible force could determine the ultimate fate of the universe is both awe-inspiring and humbling. It reminds us that we are small players in a much larger cosmic drama, one that has been unfolding for billions of years and will continue for billions more. Yet, despite its overwhelming scale, dark energy also connects us to the universe in a profound way. The same force that pushes galaxies apart also acts on every point in space, including right here on Earth. While its effects are imperceptible on small scales, dark energy is still present in the space around us, influencing the very fabric of the reality we live in. It's a reminder that we are part of something much larger than ourselves, a universe whose mysteries we are only beginning to unravel. In the end, trying to comprehend the scale of dark energy is like trying to grasp the infinite. It's a concept that stretches the limits of our understanding, challenging us to think beyond our everyday experience and to consider the universe in all its vastness. Dark energy operates on the largest scales imaginable, influencing the entire cosmos and shaping its destiny. And in doing so, it reminds us of the extraordinary nature of the universe we inhabit, a universe filled with wonders that are as mysterious as they are magnificent. As we journey through the cosmic dance of dark energy and the mysteries it holds, we realize how much there is still left to uncover about our universe. From its elusive nature to its colossal influence on the fate of everything we know, dark energy challenges us to think bigger and deeper about the cosmos. If this exploration has ignited your curiosity and expanded your view of the universe, then don't miss out on future discoveries and insights. Hit that like button to show your support for our quest for knowledge, and subscribe to the Quiet Universe channel to stay updated on our next adventure through the stars and beyond. Remember, every click helps us bring you more captivating content, unraveling the mysteries of the universe, one video at a time. Until next time, keep gazing into the night sky and wondering about the wonders that lie beyond.